So we are on the last portion of our module 1. So we're going to finish it. We might have a short meeting today. Okay. And then next meeting, we're going to have the second module. Okay, of whose link I already what we call posted in Canvas. Okay, so the last part of module 1, which is the main lecture on chapter 8 in the recorded slides that I made available in YouTube. So it's mostly about this what we call periodic table. Okay, so the trends in what we call the periodic table. So I would suggest when you take the quiz later on to have a copy of the periodic table. It's going to be helpful if you have them. Okay. So the periodic table that we have at present looks like this, and as you could see, some of the elements has been known since ancient time. Okay. And more elements were discovered as time goes by, and most of the synthetic ones were just available from 1965 to the present. Okay, so if you're going to look at the periodic table, it follows basically the electron configuration that we have discussed last time. Oh no, my internet is unstable. Okay, so if you're going to look at this, so this is the ns2, so ns1, ns2, so we could say this is the s orbital, and then here, okay, you have the so-called p orbitals. So an s orbital can accommodate 2 electrons at most, a p orbital can accommodate 6 electrons at most. And if you're going to look at this, you have an n, which is just the principal quantum number. Now the d orbital that you have is the one here, and the way that you're going to put the d here, it's just equals to n minus 1. So this one here, you could say this is 3d, this is what? 4d, and so on. So that's the d, and then you have the d5, and then what we call the d10. Now, when you go to the f that is introduced on the 6th period, so the f usually has n minus 2. So you have 6 minus 2, that will give you this what we call 4f. So that's how the periodic table looks like. And if you're going to look at it, usually the s and the p orbital, that's what we call the representative element. And this one is what we call the transition element, and this is the inner transition element. But if you look at here, you can say that's the lanthanide and this is the actinide. But in my other lecture, I will say representative element for s and the p orbital, transition element for the d, and inner transition elements for the f orbital. Okay, so we talk about electron configuration from our last synchronous class. So we can also incorporate here what happened when your atom became ionized. So ionization, or the formation of cations and anions, is just the addition or removal of electron. Okay, so if you have a sodium what we call sodium atom, when it becomes positively charged, what happened to the electron? Remove or added? Anyone?
Removed.
Okay, it was removed. Sabi nga nila, to become a positive person, remove all negativities. So if you remove the negative electron, it becomes a positively charged. And if that happened, there's no electron in the 3s orbital. And the electron configuration now is similar to that of the noble gas preceding sodium. The same thing with calcium. If you remove 2 electrons, okay, so you lost the electrons there in your outermost orbital, and you because have what we call an electron configurations of the noble gas before it. The same thing with aluminum. Now, atoms that lost electrons so that they form into a cation, they have a noble gas outer electron configuration. And if you go to the next module, that is good because when they become ions here, they become more stable. Their electron configuration is similar to the noble gas. One characteristic of a noble gas is they are stable. That's why history said you call them the noble gas, okay? Because they don't interact with other elements. Just like the noble people, they don't interact with the common people. Now, on the other hand, if you become negatively charged, it means you're adding a negative electron. Your hydrogen, when it becomes H minus, so that means there's an electron that is added there, and it became, its electron configuration is similar to the duet, the one that contains 2 electrons. Now, if it's a fluorine, so there's a 5 electron in the p orbital, so it becomes negatively charged, so that means 1 electron is added. It has an electron configuration similar to a noble gas. The same thing with oxygen. When it becomes oxide, okay, it becomes neon. Or an electron configuration similar to a neon. Problema ko yung internet ko stable. Nakikita niyo ako?
Yes po, sir, pero malag.
Nagcha-choppy lang.
Putol-putol
Choppy
po, sir.
Oo, kasi lumalabas dito. Slow daw internet ko. Lalaro na naman ata anak ko. Kanya PS5. So here, atoms that gains electrons, they form into a cation, and most of this cation, if not all, has an electron configuration similar to that of the noble gas. And if you go in our next, what we call module, okay, there's a talk there about this octet rule. So atoms lose or gain electrons to have 8 outermost electrons, similar to the noble gases. So if you're going to look at the cations and the anions of representative elements, group 1 will form a positive 1, group 2 plus 2, group 3 plus 3, group 7. 7 minus 8 will give you negative 1. Group 6, 6 minus 8 will give you negative 2. And sometimes group 5 minus 8 will give you negative 3. So all the positively charged, they have the electron configuration of the noble gas before them. All the negative charge, they have the electron configuration of the noble gas after them. So if you have fluorine, it becomes fluoride, its electron configuration similar to neon. If you have oxygen, it becomes O2 minus, its electron configuration is similar to neon. And in this case, we can say that they are isoelectronic with one another. When we're talking about isoelectronic, iso means the same, electronic means the electron. They have the same number of electrons and the same ground state electron configuration. So we could say sodium ion is isoelectronic with neon. Aluminum 3 plus is isoelectronic with neon. Okay. The fluoride ion is isoelectronic with neon. What does it mean? All of them has 10 electrons and all of them has the same electron configuration. So you might have some question about which of the following is isoelectronic with this element. Okay. So what is the neutral atom that is isoelectronic with H minus? Anyone?
Helium.
Okay. So do you have here helium? When you say isoelectronic, they have the same number of electrons and the same ground state electron configuration. So sure points ba to? Kung may lumabas? So whenever we're dealing with the so-called transition metal. So yun yung nasa gitna ng periodic table. When you remove an electron out of this transition metal, the electron would came from not the D, but the s orbital first, followed by electrons from the d orbitals. The main reason there is the s and the p are the outer more, we could say they are outer orbital. Okay, so if you have an Fe, if you form an Fe2 plus, the electron that lost first is the one in the s, and it become Fe3 plus, so additional electrons come from the d. So that's the only time the d electrons from the d orbitals starts to lose, when all the s orbitals are already lost. So the same thing with manganese. If it's for manganese 2 plus, okay, mauna yung what we call s orbital na mawawala. Now, let's talk about this effective nuclear charge, or the positive charge felt by the electron. So SEP is just equals to C minus shielding constant. Okay, so usually the shielding constant is higher than 0, but less than the atomic number. Or we could say that C there, that's the number of inner or core electrons. Okay, so if we're going to look at the SEP value, so the C is just the atomic number. So from left to right, it increases. Now the core electrons there, this we could say is the one that contains the NS2 NP6. So the core electrons for this is the, we could say, the noble gas before sodium. So that's 10. So if you're going to subtract C minus this, what we call shielding constant, this is what you get. Now, this happens from what? Left to right, and look what happened to the radius. Left to right, atomic radius or atomic size, what? Decreases. Okay? Another explanation that we can have here is, how do you correlate C? C is what? Number of what?
Protons.
Protons. What is the charge of protons? Anyone? Protons are
Positive.
positive. Now, in a neutral atom, the number of electron is also the same as the number of proton. So what does it mean? More positive, more negative, more positive, more negative. So as the positive sign increases and the negative sign also increases, they become what? Closer to one another. And when they become closer to one another, what happened to the size?
Shrinks.
They become smaller. Diba? Okay, so you can look at the trend of the increasing SEP like this one. Okay, and then the increasing SEP on this one. So we could say in terms of atomic radius, the SEP would only play a role in L to R, but it will not play a role here. Because top to bottom, what happened to the atomic size? They increases, but it's not due to the SEP. What's the main reason why the size increases top to bottom? It has something to do with this. What is N from our previous lecture?
Principal quantum number.
The principal quantum number, which relates to the size. So as N increases, the size of the atom also increases. Okay, now there is what we call different term with what we say the atomic radius. So they said that the distance between two neighboring nucleus, but I don't know, for me, if I'm going to simplify it, that's just the distance between the nucleus and the outermost electron. Okay, either atomic radius or atomic size. If it's plural, atomic radius. Now, if you're going to look at the trends, this is how it looks like. So questions like this, I want you to be sure points. So what's a possible question? You're going to be given different element and then you're going to compare which is the smallest or which has the biggest atomic radius. So usually a comparison is like the same period and the same group. So if I ask you here, which has the smallest atomic radius, so ito yun. Okay? So if you ask you here, which is the atomic, what we call the smallest atomic radius, then ito yun. So atomic size goes maybe that way, right? So dapat sure points to. Okay? And to look at the trend in the atomic radius, maybe you look at this. So this is what? Left to right. And this is top to bottom. Klaro ba? Clear?
Yes po.
Now, what happened? Okay. What happened if you add an electron or remove an electron? What happened to the size? So what do you think happened? So let's say you have an atom and then you add an electron to it. So what happened? Positive, negative charge.
Negative.
It becomes negative. And then the other one, you have an atom, you remove an electron, so this becomes
Positive.
positive. So what happened to the size? For this one, up, down.
Up.
Okay. So the atomic radius there or the ionic radius that you have there will increase. Now for the one where you remove the electron, it decreases. And if you're going to look at the trends here, so these are what we call the cut ions. So when you remove an electron here, look at the size of the respective ions. It is smaller. Now, if you have what we call some of these elements, when you add electrons, look at the anions that they form. It's bigger or larger or higher. Okay. Now, if you're going to look at this, what happened when we go to bonding, so when an ionic compound is formed, so usually what happened to the lithium? It lost electron. And where did electron go? It goes to the fluorine. So when the lithium loses the electron, this is the size. When the electron is added to the fluorine to give you fluoride, this is the size. So cation is always smaller than the atom from which it is formed. And anion is always larger than atom from which it is formed. Okay, and if you're going to look at the atomic ionic radii, so this is how it looks like. So look at all the negatively charged. They become bigger. Did you get it?
Yes.
Question? Kung may tanong, huwag mahiya. Hindi naman kayo ipipenalize kung may tanong eh. Sorry. Now, the addition or removal of electron, there's an associated energy on that. So whenever you add or ionization, and whenever you remove an electron, You need energy to do that. So ionization energy is the minimum energy required to remove an electron from an atom in its ground state. Okay, so you have an atom, you apply an energy there, so you remove an electron. So if it's the first electron to be removed, that's the first ionization energy. You apply more energy, you remove the next outermost electron. So that's the second, the third, and the trend that they have there, the more electron that you use, the higher the ionization energy. And sometimes the increase in ionization energy is just so high. Okay, so for instance here, look at this. Look at this. Look at this. Look at this. So here you have what? 1s1. So if you're going to remove the electron there, you form 1s0. Here you have a 1s2. So first ionization energy, 1s1, second ionization energy, 1s0. Now here you have what? 1s2, 2s1. So after you remove it, you form what? 1s2. Okay. Now, to remove one of the energy there, you're going to need, to remove the electrons in 1s2, you're going to need energy more than 10 times when you remove the first electron. So that means if you have a full s orbital, you're going to disturb a very stable system. And when you disturb a very stable system, you're going to need a very high energy. Okay? And if you're going to look at the trend of this first ionization energy, this is how it looks like. There's some anomaly here, the transition to s to p orbital, and then anomaly here, the transition of p3 to p4. But in general, ionization energy, what? From left to right.
Increase.
It increases. And from top to bottom, so if you're going to look at this one, ionization energy decreases. Can you relate ionization energy with atomic size and atomic radius? Yes or no? Pwede ba natin i-relate yung ionization energy with atomic radius? Yes or no? The answer is
Yes.
yes. I don't know if it makes sense. The smaller your atom is, the more stable they are. So if you're going to remove an electron out of it, you're going to apply a lot of energy. Okay? Compare it with so big to the point that the outermost electron felt that they are out of place, so it's easier for them to be removed. Right? So that's the relationship that we could say with ionization energy and atomic size. So the smaller the atom, the more stable it is, the higher the energy that you need. Okay? So if we're going to look at the trends of the ionization energy, it's like this. The reverse of atomic size. Now, if ionization energy deals with removal of electron, electron affinity deals with addition of electron. So when we're talking about ionization energy, mostly it happens on metals. When we're talking about electron affinity, mostly it happens on non-metals. So again, the rule that we can have here, the more stable the atom is, or the smaller the atom is, the higher is the electron affinity. Okay. So if you're going to look at this, what does this mean? If you're going to add an electron here, that is an exothermic reaction. So that means the amount of energy that you have there is the reverse of that. And if you're going to look at the value here, it's a little bit, we could say, contains a lot of anomaly. If you're going to look at the noble gases, it's less than 0 because they're so stable. But if you're going to look at the energy that you have here, so you see the value. But I always remind my students, just know the concept of your electron affinity and look at the overall relationship that they have. Left to right is some sort, is the anomaly here. So as you could see, yung s orbital from S1 to S2 going down, and then from P1 to P3. I don't know if you see this. So this is S1 to S2, and then P1, P2, and then P3, and then P4, P5. So they said the trend here is still similar to what? Ionization energy. Is that when you disturb a small atom, you're going to spend a lot of energy, whether to remove or to add electron. Okay? And I think that's all that I have for module 1. This rest is just about the different group elements. Tanong. May tanong? So we're done with module 1. And if you're going to look at what we call the canvas in the announcement, I already put the links to module 2. And again, there's 2 chapters. We're going to go to bonding next week. Tanong. Okay lang ba yung kayo sa setup natin? Is everyone okay with the present setup? That we meet every meeting even for what, 30 minutes?
Yes.
Yes,
And
po, sir.
And don't be discouraged. I don't know if you look at the recording. Usually the B2 has a shorter recording than the U2. Because I'm presenting the same material. So mas mabilis na ako by the second time. I don't know if you notice it. Okay. But I have to have this type of setup that we meet synchronously because most of you are what? Freshman, right? Freshman ba? Sino mag-ganon? Mag-thumbs up. Ang freshman. Kung ayaw niyo magpakita, hindi ko kayo ipo-force na ipakita yung mga mukha niyo. Baka iba sa inyo, hindi pa naliligo. Baka iba sa inyo, nasa ano pa, sa kama pa. Ilan sa inyo nasa LB? I-ano niyo yung kamay. Okay? Kasi may issue. So if you're going to look at the periodic table, so nasa na ba yung flatted? Hanapin natin. Okay, so platinum would be what? Here, right?
Yes po.
So, ang titignan mo lang dyan, if ever you see it, if I'm not mistaken, this is just that one, and 5D, 1, 2, 3, 4, 5, 6, 7, 8. That's it. Kasi yung F is much more inner. How do we define valence electron? When you say valence, what are we talking about? Yung outermost.
Outermost.
Electron. Yep. So, strictly speaking, usually ang outermost ay yung S tsaka P lang eh. Wala lang tayong choice kasi nasa D area siya. So kapag nandoon yung F, yun din yung valence electron natin. Merong F. Clarify? Okay ba?
Okay po, sir. Thank you po.
Any more? Do you have any question? Okay, mahiya. You still have what? 47 minutes to do the quiz. Baka iba sa inyo, nag-quiz na eh. Okay? So if none, para ma-download ko and hopefully ma-post before kayo mag-quiz. So if none, have a great weekend.